All right. Hi, I'm Jacob. You may know me from the Existential Risk Alliance. My project was on investigating supervised contrast consistent search, or CCS. I'd like to thank Tillman, my manager, and to a large extent my mentor, and general cool guy. This is the Shoggoth. It is a representation of language models as an alien intelligence governed by unsupervised learning and not much else. We patch it with supervised fine-tuning and RLHF, but realistically there's only so much that can do. For instance, we might want guarantees like honesty, the language model saying what it actually believes. Fun anecdote. In a lot of their first papers and mission statement, Anthropic advocated for, I think it's helpful, honest, and harmless language models. In recent papers, that has been restricted to helpful and harmless language models. Wonder what's going on with honesty. As a first pass on what we might try to do, we can use deep architectures like BERT, presented first by Google in 2018. It is a method to take in a bunch of words and output a vector. Why do we want a vector, you might ask? Because we can run classifiers on them. In this case, we're using something like a neural net. We can also use something simpler like a linear classifier. The point is we get this numerical judgment, a probability judgment, of whether something is spam. In our case, we don't care about spam in like this email context. We care about truth. Replace spam with truth, and you have the next thing, CCS. CCS is essentially this BERT plus classifier architecture on steroids. Let me describe the steroids. The first improvement is this method of contrast pairs. Say we have some question like, are cats mammals? And we want it answered. And two, we could just run BERT on like the question, but instead we do this clever trick where we answer the question yes, and run BERT on that. Important context, this feature representation, internal model activations, is something like BERT. Some deep language model representation of your sentence. And then similarly, we can answer the question with no and run BERT and get some like deep representation there and do some comparative analysis on these contrast pairs. The second innovation, which we will not be using, is unsupervised clustering. Instead of having questions of the form, are cats mammals, and answering them as yes or no, we instead take a bunch of examples, separate them into two clusters, and argue whether one cluster is true or one cluster and the other cluster is false. They do that with this probability judgment for the question answered with yes and no, and try to make the probability sum to 1 because exactly 1 can be true. Don't worry about that. I don't use it. I also don't like it. Moving on to the theory of change of methods like CCS, Colin Burns has a EA forum post about it. It argues a few points. One, deep learning has special structure that we can exploit for alignment. This is basically the idea behind BERT. It's sort of a contingent fact of the world that we can just build a thing that takes in a sentence and tells us everything we might want to know about that sentence, which is extremely convenient for methods like classification or CCS. Another point, unsupervised methods are more scalable than supervised methods. My understanding of this is the problem of it's really hard to get a godlike AI to tell us what it means. And so it's very hard for us to say, give it supervised labeled data to train on. We just don't have the capacity to process its thoughts. If it can process its thoughts for us and give us truth and falsehood for free, we don't have to deal with that problem, which is incredibly convenient for us. And the thesis here is we may be able to recover superhuman beliefs from deep learning representations in a totally unsupervised way. This is the holy grail. This is, we get a God AI, we want it to tell the truth, we don't know how to make it tell it the truth, and it just does tell the truth. With minimal human oversight, with literally no supervision, or almost no supervision, which is excellent. This is currently completely unsolved and people don't think it can be solved. And so if this works, fantastic. Moving on to experiments. Some notes on experimental design. We use the DeBerta models, which are essentially BERT plus some clever training tricks. Some differences from GPT-like models, which are really the ones we care about. First of all, our models are encoder only. They take in sentences and give you a vector, as opposed to the next token. Also, these models are small. The largest model I tested on is 10 billion parameters. GPT-4 is widely rumored to be over 1 trillion parameters. As a data set, we use IMDb. It is a data set of movie reviews. It's pretty common in literature. It tests for positive and negative sentiment. An hour before this presentation, Ria asked me, wait, this doesn't sound like truth-false. This sounds like sentiment. To which I respond, yes. Hard to test truth. See Anthropic's difficulties earlier. So as a classifier, we use logistic regression on differences of contrast pairs. This is not quite what they do in the paper. I think this is a principled thing to do for a few reasons that I won't get into. This is also a supervised classifier. Note that we're not using the unsupervised tricks of CCS, which is an inherent limitation on our study, but makes a lot of things a lot easier. Moving on to the experiments themselves. First, is truth salient? This is sort of hard to operationalize. It's weird what we mean by salient. The version I chose to test is what % of our features, the things extracted from some BERT-like featureizer, correspond to truthfulness, the thing we're trying to measure. This is analogous to like an R-squared measure of our data, or like a principal component analysis of our features. We find that over like a variety of subsamplings and random initializations, trying it a bunch of times, we consistently get about 5 to 10% of variance explained. The paper claims that representations of truth can often be found by taking the top principal component of a slightly modified representation space. This is a little verbose. It basically means, in an unsupervised way, we can just kind of like guess which direction truth must be by like a thing, a direction, a feature that's pretty salient and bimodal, because like truth and false, and it just works. And my studies find that this is credible, though I didn't test it directly. We also just see that CCS works. It correctly classifies true or false, so it must know something about true or false. It consistently gets 90% in our tests and gets 90% plus on a variety of data sets tested in the paper. Thanks. Next question, is truth linear? This is pretty easy to operationalize. You see if nonlinear classifiers can do better. We tested support vector machines, SVMs, because they are under-parameterized and so robust against overfitting, and the baseline is logistic regression as discussed earlier. Both methods solve IMDb. IMDb is kind of easy. To make it harder and get a better test, what if we took the difference of means between true and false things and ablated it out? The linear classifier is like just horribly confused. Like the whole thing it was looking for is the difference of means. That's like the linear separation, and so it has nothing to look for and predictably fails. Sort of importantly here, SVM succeeds, which means that there is some nonlinear feature to the truth versus false data that a nonlinear classifier can find. More on that later. Next question, do contrast pairs help? Again, what if you ablate them? Salience decreases by 5%. Salience was like 5 to 10% to begin with, so there's almost no salience to data without contrast pairs. Accuracy decreases slightly. It was pretty high to begin with, not a huge jump. Sort of more obviously, the total variance of our feature data dramatically increases once you remove contrast pairs. Compared to a contrast pairs baseline, if you don't use contrast pairs or only use one side of it, there's like 30x more variance, which means that in some sense the trick of choosing contrast pairs that were very close in feature space and subtracting them from each other like reduces variance by a lot and so increases salience of the thing you're actually trying to measure. Next question, does scale help? The most obvious thing is that salience decreases dramatically with scale. At 100 million parameters, most of your feature data is just encoding truth. At 10 billion parameters, almost none of it is. Surprisingly, accuracy seems preserved. Small models usually do worse because they're small. But even the smallest models we test solve the IMDb data set. The intuition I have is even simple models recognize truth, and complex models tend to recognize a lot of things that aren't truth that we're not looking for. Big questions here, does this generalize to other, presumably harder data sets? And to what extent is this related to the training task of the DiBerta models? Maybe these models are particularly good or particularly focused on truth, for instance. Some conclusions, all pulled from existing analyses of CCS. One, there is a less wrong article by Scott Emmons titled Contrast Pairs Drive the Empirical Performance of CCS. Our findings corroborate that. They work. They increase salience, they decrease variance, they slightly increase accuracy. The CCS paper claims that truth is a salient feature of language model representations. We find the same. We don't use their unsupervised clustering trick, but truth indeed seems salient. Another relevant conclusion is that model scale doesn't seem to help. We have not found as much of this in literature, and to test this, you'd have to look at more complex data sets for which you'd expect model scale to be most useful. As some future work, first of all, there exists a pretty clear generalization to the unsupervised case. Most of the reason I used the supervised methods I did was for convenience. There exists this method called latent discriminant analysis and other things like it, which basically let you do unsupervised methods in cases where supervised methods would be more natural. Another important question is how much does nonlinearity help? We find some evidence that it helps significantly. I plan to do a literature review and a comparison study to CCS. And a last point of future work is, can we reliably deploy CCS-like techniques with small models? I think the critical question here is, can small models solve the relevant data sets? Like, if the small models just don't understand what it's trying to do or isn't smart enough to complete the task, there's no hope. No amount of like CCS-style contrast pair scaffolding will solve this for you. Another question is, why do we want small models? The standard answer from literature is that small models are like easy to use, widely accessible, convenient for a variety of reasons, compute efficient, and all of these are like kind of good reasons, but it bears thinking harder about what exactly we want from them. And as an epilogue, sort of natural follow-up study, can I beat CCS? Importantly, I need to choose a data set that CCS doesn't just solve. I chose BoolQ, it's studied in the paper. It's essentially like a yes-no data set, and CCS can't solve it. So can I solve it? I tested the linear regression method I described, my SVM implementation, and a more kind of complex linear regression estimate or implementation in the paper. Nonlinearity seems to do okay. More findings needed. Hopefully I can publish. Thank you, and would love to hear questions.